1, 2, and 3. So let's begin. So today it's gonna be like more frames, you know. So this time I'm just going to spice things up by adding more load to see if you can handle it. Okay. So this one has more load. Okay, and you see the another difficult point, maybe if you think it's difficult, is that now the two supports are not at the same level, so you need to be very careful when taking the moment. Okay, and right now to try to be smart on calculating the force, maybe it's not so smart at all. So we need to try to simplify this by perhaps taking the moment at the hinge first, because there are two reactions at the hinge. So it would be smart to try to eliminate those first. Okay. So before we do that, let's give it some name, shall we? So that we can refer to the members. So let me call this A, B, C, and D. You know, you guys have very creative ways to call your friends, and just I try to do things maybe clockwise like that, but you know, it doesn't matter really. But I just, you know, if you name things properly, maybe it should help your organization when you do the problem, especially under the time constraint, the exam, that is. Okay, so if you name your structure well, you know, your thinking, your analysis will be more organized, and then it should help. Okay, so let's go. We are going to have one reaction here. We are going to have another reaction here, and then one more here. You see, I kind of like to draw the support because it will show you how many reactions you're going to have. Okay, so without further ado, let's take a sigma MA equal to 0 first. I think there's another question from last time as well. I don't know if it's in the class or in the session. I think it's in the part, right? Asking me about the order of writing. You know, I am, because things like this are in my say streaming of thought already. So from time to time, I may tend to go not very well organized. You can ask me to go slowly and to try to show more calculation. And more importantly, if you cannot catch me up during the session, you can ask me to stop. Okay, please do so. Otherwise, I wouldn't know. So okay, we are going to take. I'm sorry, you see that? We're going to take a sigma MA equal to 0. Okay, so now we have this uniform load, 200 kilogram force. So that is going to do the clockwise for me. So let's say 200. That's the load, and multiply by 6. That becomes a point load, right? So it acts at the location 3 meters or half of 6. From time to time, you know, not from time to time, let's say from this point onward, you see when you take the moment of the uniform load, you can see the form here that it's gonna be exactly like WL, then multiply by L over 2. So I wish that you would know now that if you take the moment at the end like this, the uniform load will always give you the moment equal to WL square over 2. So I tend to write it like that more because first of all, it's quicker. And second of all, I want you to feel how the load, you know, affects your structure. Not just if you keep doing this all the time, it's just like, when will you feel it? Excuse me. Okay, so if I write WL square over 2, you should know that, okay, it comes from this. So that's the first load done. So for those of you who still struggle a little bit, we're taking the moment at A. So this one, the uniform load, will give you the clockwise, and this point load will also rotate your frame like this. So it's clockwise as well. So that plus if I say that 200, this is supposed to be 8,000, right? Be careful of the unit. So I think it would be easier for me to change this into, let's say, 0.2. Okay, and then we're gonna have 8 tons. And then this is the load. So the moment arm will be 4, right? Now, this is a mess, so I'm just going to erase this. Okay, next one is this one. The 5 ton. This guy is, when you take moment at A, this guy is going to give you counterclockwise moment. And therefore, it's going to be -5 multiplied by 3. Okay, the next one is this 3 tons. But look at that, these 3 tons will exactly pass point A. So if you want to be thorough, you want to complete everything, you may want to write something like 3 and then multiply by 0 because there's no moment arm. Okay, and if you assume the reaction at D to be the upward force, you will now know that the reaction at D will give you the counterclockwise moment about point A. So that is minus RD, and then the moment arm perpendicular to the force is 8. Okay, that is 0. So after this, what we can do is we play some calculation music. Okay, and then you see that RD is equal to the 2.575 tons. Okay, so that T as a ton, not the function of time. Okay, how can I see my own screen? Seems difficult. Okay, nothing matter. So now you may be so tempted to use sigma Fy equal to 0 here. I advise against it. You should try to take moment one more time, or if you do wish to use sigma Fy equal to 0, you would know that you have like 8 tons downward here, right? So it's 8 minus 2.575 minus RA equal to 0. So now you know that RA is 5.425 tons. Sorry. Now, what you should do before you head out and try to complete this is that let's check it one more time. Sigma MD equal to 0. For example, just to see that, you know, things are going okay for you. Or you can also try sigma MD equal to 0 to solve for the HD. Okay, because you can just easily say that, you know, your HD is equal to 8 minus the uniform load. But let's say, okay, HA, if you take moment at D now, okay, you're gonna have HA, which is this, multiplied by 3, right? Your HA is this one. You know, I tend to use the H for the horizontal reaction, so that's HA. So this becomes the moment arm 3 here, and this one gives you the clockwise moment. So it is HA multiplied by 3, okay, plus that is 5.425, and it gives you clockwise moment as well. So that's 5.425 multiplied by the distance, which is now 8. Okay, and then you have the uniform load, 0.2 multiplied by 6 squared over 2. Okay, and then minus 8 multiplied by 4. This term is the moment caused by this point load around point D, right? This point load, okay, coming in this direction. So it caused the counterclockwise moment around point D. And then you have this 5 tons here that will cause another counterclockwise moment, and multiplied by the moment arm, which is now 6, and then minus these 3 tons multiplied by 3, that is 0. Okay, and H from this equation, we have HA equals 6.8 tons. Don't forget to check your sigma fx as well. If you do it this way, there's so many ways to solve the reactions, but before you proceed to do more serious work, just make sure that your reactions are correct. Remember that wrong reactions will give you absolutely wrong answers from this point onward. Okay, and we grade your work based on the rubric. So if you complete the reaction, if all the reactions are correct, you get 20%. And if you mess up one of the reactions, you will not reach the first 20% and the rest will be garbage. So the overall points of your problem will not exceed 20%. Okay, so once you have completed this, let's move on to try to complete your free body diagram of the 3 members. Remember, if you got correct free body diagrams for all 3 members, you get another 20%. And please try to make sure that you get all the free body diagram of every member before you start working on your shear force and bending moment diagram. Okay, so let's go. Let's see the first one. Okay, it's like that. And we have the, okay, it's a good picture, but when I do the handwriting, my uniform load tend to become something like this. Okay, hope you forgive me for that. And we have the, okay, trying to look for the load. We have 5.4 to 5 going up, and we have 6.8 actually goes this way. Okay, so that's the forces we know from the calculation of our reactions. You know why we have to calculate reactions first in this case? It's because the reactions are our unknowns. Okay, get this big picture. At the beginning of the problem, you have 3 unknowns that you need to know first. And for the purposes of the determinate structure, those 3 unknowns tend to be the reactions of your system. Okay, and it means that this is the basic system. Those 3 unknowns can always be solved by simply using those 3 equilibrium equations. Okay, if you have more unknowns than this, you're going to have to take the next step and obtain more knowledge to try to deal with that. Okay, so this is the first step that we know. We got the reactions from the first process, so it's time to find the, let's say, the internal forces in this member, especially at joint B. Okay, so you know, sigma, I can see that. I don't, it's part of the question. You can say by inspection, or you can just say sigma Fy equal to 0. So now you know the, I say, ooh, okay. I don't know how to call that. Say FB is 4.5 tons, right? So now we know that this has to be 5.425 Anyhow, I don't know how to name it because it comes really naturally. You guys should know that. But now it's just sigma fx. So you should be more careful because when you take sigma fx equal to 0, you must include this uniform load as well. And you see, the direction of this uniform load is actually the same as the reaction. So let's say HB now is going to be equal to 6.8 plus 0.2 multiplied by 6. So, you know, naturally that should give you 8, right? Because you know it should be equal and opposite to the forces on the right column. So that is now 8. Okay, so now don't forget that because in the vertical directions, you know, this is what we generally call column, right? So the axial forces, they coincide, so they don't generate moment. But the problem is with the horizontal forces. This 6.8 is right here. This uniform load is right there, and the 8 is right there. So there must be moment to balance this member from rotating until eternity. Maybe I should write this down as a point B here. And then point A. So we now have sigma MB equal to 0, right? To try to solve MB. Just a small note on B here. Okay, so you can take moment a day, and you can take moment at B as well. See what I did. I take a moment at B. Okay, so yeah, sigma MB equal to 0. So we now have 6.8, which is the reaction, multiplied by the length of the member, which is 6 meters. Okay, so 6 meters multiplied by that thing again, 0.2 multiplied by 6 squared over 2. Okay, and supposedly minus MB equal to 0. So there you're going to have MB, and you will know that it's not going to be 0, highly unlikely. And this is equal to 44.4 ton meter, you know, after some calculation music. Of course, you should see the direction that the 6, if you take a moment at B, which is this point, you have the uniform load trying to rotate the member like this. The 6.8 is also trying to rotate your member like this. So naturally, you should have the moment that will resist or counter this movement. Okay, so that's the direction of your moment. Naturally, you can also figure it out from your calculation, correct? But you know, the more you do it, the more you can feel it, right away. You don't need to look at the numbers. Okay, so that's what we have. So true to my words, I'm just going to skip to the next page because I'm just going to leave the space on the right side of the column to draw my diagrams. Okay, so I'm just going to skip to the next page and try to complete the free body diagram of member BC. So now we have member BC here. Okay, so what do we have here? Again, I'm trying to use the red color as the forces that transferred from member AB at joint B. Okay, so we can go back here. We see 5.425 as the downward vertical force. So naturally, this is going to be 5.425 tons upward. Okay. There is not a presence of the point load at the joint B. So that means we can take this horizontal shear on the column, which is equal to 8 tons, to become the axial force on this member right away. So that's 8 tons. So far, so good, right? And now we have the clockwise moment of 44.4 ton meter. You guys be careful when you work on this, okay? Because you may change the color when you use the pen, you use iPad or whatever, so that it will help you recognize which one is moment, which one is the shear, which one is the axial force. But for me, I use the same color. It's a bit more difficult to recognize, but then you see, I have the unit so that I know this is moment. So we have the clockwise moment here. That means we should have counterclockwise moment here. This is 44.4 ton meter. Okay, and don't forget that we also have the external load here equal to 8 tons. All right, so we have 8 here. So if you wish me to do it, I'll just write it for the sake of completion. I'll leave some space for my shear force and bending moment diagrams here. So okay, sigma fx equal to 0. I can say that I know my horizontal force at C will be equal to 8. Okay, so that's 8. And now sigma Fy equal to 0. Say VC, it's going to be equal to 8 minus 5.425, which is of course the vertical reaction of the frame at D, right? How much is that? 2.575 tons. Give some units as well. So that is 8. That my 8 looks horrible. That is 8. That is 2.575. And then again, because we have the presence of the horizontal load on member CD, so chances are you should also have moment at C as well. So we're going to take sigma MC equal to 0. Okay, so be careful, because when you take moment at C, you must always include this as well. You know, that's the moment. So it's on your free body diagram. So you see, up to this point, you see that doing the frame is no more than putting the knowledge of your free body diagram to the extreme. Okay, so now we have, let's say, I'm gonna do, so to help someone, counterclockwise as positive. Okay, so I'm gonna begin with this 8 tons external load. So that's 8 multiplied by 4, right? Take moment at C, the distance is 4, plus the moment itself, 44.4 ton meter, which is the end moment. Okay, you can say this is the end moment because it's the moment at the end of your member. And this is what we call end moment. Okay, include that. This is your end moment. And then you have to count for this shear, but it's going in the clockwise direction, this shear. Like that, right? So it is minus 5.425 multiplied by 8. Then let's say my MC is in this direction, so minus MC equal to 0. So playing some calculation music, you know that MC is equal to 33 ton meter. It's positive. That means I assume in this equation that my MC is clockwise and it comes out to be positive. So that means my MC is clockwise. 33 ton meter. So that's the completion of the second free body diagram. So I'm just going to move to the next page and try to complete the free body diagram of member CD. So let's write this as BC as well. You may want to put it on your top corner, this is member BC, and okay, this is member AB. And next, last one is member CV. Now, this is where the excitement begins, because we now have all the forces for both ends. So, you know, all things must come together in this member. It's not very straight. Give me, you know, I kind of like to draw the roller like this from time to time. I can add as many wheels as I want, you know, just to make it look like a roller blade. But mind you, I have drawn a roller like this since before the time of the roller blade. So that is it. Okay. We what is the color of the reaction that I use? Okay, it's a red as well. So oops, sorry. So we now have the reaction here from the first step of our calculation to try to obtain the reactions. We know it is 2.575. And look at what we have at the end of member BC. Go back here. Oh, that's 2.575 going up. So this force is going to member CD, 2.575, but going down, right? So look at that. Voila. Our sigma Fy is correct, right? But not just that. You have the, oh, that looks like a B, but it's a horizontal force at the end of member BC equal to 8 going to the left. So this one goes to the right to member BC. 8. And then you also have this moment at the end, 33 clockwise. So it comes here 33 ton-meter counterclockwise. And then what else we have here? We also have this and then that, right? If it's a lean column, generally, you know, the moment should be 0, but this is a lean column with the external force. So there must be moment at C to help the equilibrium, okay? And this is 5 tons. That is 3 tons. So it's time to hold your breath and check your equilibrium just by taking sigma MC equal to 0. And now you know you have 5 tons. This one that will give you the clockwise moment. So this is 5 multiplied by 3. And then plus 3, this one. I should, okay. 3 multiplied by 6 minus 33. Is it 0, folks? Has to be, right? But you just can't imagine things. You must prove it be so. That is 15, that is 18, so that's 33. And yes, we have 0 sigma mz. That means everything is correct. We have the correct and complete free body diagram. So now everything has been proved to be correct by the correct free body diagrams for all the members in the system. It's time to proceed to obtain the shear force and bending moment diagram of each member. Okay. So now, ladies and gentlemen, what do we have here? Now, when you see the free body diagram, can you imagine how your member is going to deform? You know, you have the load pushing the member to the left, and then you have the moment and try to maintain it. It's balanced. So chances are your deflected shape should look something like this. Say, You see? And then the bending moment diagram, we should just try to hold things in place. So where would the compression be in this case? You can look at the direction of your moment and you see that if I rotate this member clockwise, okay, let me try to draw it again. I can look at this member like this now. It's really hard to draw the horizontal line straight, you know. And then we have this, and then we have that. Okay, so I can look at this member like this when I want to draw my shear force and bending moment diagram. Correct? With this. And you see, where would the compression? Where is compression? Actually, I think, where's the compression?
Of the beam, right?
It should be down here, right? Compression. Am I correct?
Yes.
Yeah, so that means this is where you should draw your bending moment diagram. That's where the compression is. So you can look at this beam like this and then try to draw. Now, I think it would be easier for you if I draw it from this picture. You have the downward shear, begin from the left. So if you have a shear like this, down and up, that's a negative shear, right? And of course, that is, oops, I'm so sorry. What a terrible mistake. We have the minus 6.8 here because that's going down, right? I completely forgot that we had the uniform load. So the uniform load will take this down linearly until we have minus 8. That is your shear force diagram. And you have the negative area, right? So naturally, this will bring your bending moment diagram from 0 down to the value of what you have there, minus 44.4. This is shear force diagram in tons. And this is bending moment diagram in ton meter. Let me draw it again here so that it looks more complete. That's our shear force diagram. Okay. Okay, 6.8 and then 8 and then bending moment diagram. Oops. Okay, that's gonna go like that. Oh, geez, sorry. It's scary. Minus 44.4. Okay. Again, you can flip this beam, and this is the diagrams drawing by looking at this member from this direction. So that's my eyes. Okay. You can also look much like the eye, but anyway, you can look at this member and draw the diagrams from this side as well. Okay, it's the same thing. So let me do that again for you. I need to erase something because I'm running out of space. I want to keep it in this page. Okay, so let me try to erase this and try to squeeze this in, okay? Let's change the color as well to pink maybe. So if I can also draw, now I am drawing this member AB's shear force and bending moment diagram by looking at it from this side, okay? So when I look at it from that side, I will see this moment going up like that. And I have the downward shear, and then I have this, okay? And then that. And also this is the upward, okay? So again, you know, I begin from the left. Now I still have the shear with the sign convention of, you know, down on the left and then up on the right, which is the negative shear, right? So my shear force diagram will look like this. The same. And the uniform load will bring it down. So from 6.8, we end up with 8 here, okay? And now, look at this. We have this time the sign convention of the moment that is a positive moment. You see? So this time, this guy will have to start from the positive value of 44.4 because the sign convention here is the positive. Remember this? Is your positive sign convention. So it begins with the positive value, but because of your shear force diagram is negative, so this will be brought down to 0. Okay, now the moment here may be positive, but you will see that this is the moment that is, I think I'm sorry, you know what, I made a mistake because I draw the, so my apologies. Let's begin that from the beginning. Sorry everyone. The moment is correct, but the load is wrong because of the way I draw the, it's like this. So my apologies. Let's okay, because this is 8. I got confused myself. And this one is upward. Okay, that's more like it. Okay, that one is 8 downward, right? That's 8, but it's going upward. So if we begin here, our shear force diagram here should be in fact -8. And then the uniform load is becoming the upward one because in fact it goes to this direction. So if I look at it from that direction, it's like this. So it's -8 and it goes up to become -6.8. Okay. And now you have the positive moment instead, but it will be brought down to 0 because of this negative shear force diagram. So even so, you can see that now the bending moment diagram may look positive when you start drawing by looking at the member from the left. But the point is that it's on this side of the beam. See, the bending moment diagram is on this side of the beam, of the member. Okay, and it looks like this. And if I flip this whole thing, if I flip this whole thing clockwise for 90 degrees, this is exactly what we have for bending moment diagram, but you bar the fact that shear may look a little bit different. But that's because we start from a different place, but the bending moment diagram would stay the same. Okay. So is there any question? So it doesn't matter where you start or where you look from, you know, the bending moment diagram will always be, you know, applicable at the same location. I mean the same, on the same side, same value. That's the whole point. Now, any question? Hello? So, okay, let me stop the record first.